This video is going to cover shear strain and deformation. Now, shear strain we like to call gamma, and that is, we'll just write it out, shear strain. And what that actually is a change in shape. That's all shear strain actually is. It is kind of weird though. Its units are in radians. I don't really like to talk about the change in shape in terms of degrees, though mainly we are actually talking about angles. And shear is very, very weird. If you haven't already noticed, like things when we make a cut and we're looking at the cut here, we're looking at the left side, normal goes out and that's positive X direction, that's great. Moment goes counterclockwise and that's usually what we like to consider positive. And then randomly you would think shear goes up, but shear goes down. Right? Shear goes down. If you think back to it, shear was always weird. Every single thing about him, everything that we talk about with him, he's always weird. He's always just the odd, goofy man out. So because of that, he's going to kind of follow suit here. And shear, since we're talking about angles, if the angle gets smaller, so if the angle shrinks, we consider that to be positive shear strain. Okay, and if the angle gets bigger, we consider that to be a negative shear strain. Yep, he's just backwards. He is legitimately just backwards from every single thing else that we do. Shear is just weird, and he does have reasons for that, but not that we have to jump into too much this time. So again, he's just a change in shape. That's all he is. So let's go see an example and see how that works. So here we have a square. It's not really a square, it's a rectangle, right? It's 400 tall by 300 wide millimeter rectangle. And we've moved B over by 2 millimeters, and we've moved D down by 4 millimeters. And because of that, C also got moved because he's obviously connected to the two of them. So he's going to move. And then what we want to do is we want to find the change in angle of A and the change in angle of D. What's going to happen to that spot as well. So again, D went straight down and B went straight over. So C kind of did a little mismatch of both. So if C did kind of both, then let's start off with what's the coordinates for C prime? What's the coordinates for him? So horizontally, we were at 300, but we went in the negative. You notice that we have positive X over here. We went in the negative X direction 2 millimeters. So that means that our C coordinate for the X direction is 300 minus 2, so that's 298. And for our Y direction, we did have 400, but we went down 4, down from our positive Y drawn up there. So we went down 4. So 400 minus 4 is going to be 396. So that's the new coordinates of C. That's C prime's coordinates there. So what we want to do is now figure out our angle. So you notice that technically C to D is still vertically here, 400, because we're down 4. So the length there is still the same, but just horizontally things have been a little bit different. Same thing for B to C. He's just exactly opposite. So if I want to find the angle here, originally A was 90 degrees. And now I want to find out what new angle A is. We're going to call that theta prime of A. Okay, so again, gamma, our change in shear strain, is going to be the original angle A minus new angle prime A. So how do I find that? Well, I need to find his little itty bitty bits, right? There's a little itty bitty bit there and there's a little itty bitty bit over here. So how do I get those two bits? Well, I'm going to find them individually. So let's just say that we're going to call this angle between AB prime and AB original, we'll call this alpha. And we're going to call the angle between AD and AD prime to be beta. So let's find what those angles are. And to do that, those are very simply just triangles. We can even shade our triangles in. We went over 2, and this is across 400. There's our cute little triangle. Yep, there he is. So what's the angle there? For alpha, oh, we probably should have done those in different colors, huh? We'll do beta in, say, red. So alpha here, alpha's in purple. Alpha is going to be what? We have opposite, we have adjacent, that's going to be tangent. So we're going to do the arc tangent of the opposite, which is 2 millimeters, over the adjacent, which is 400 millimeters. Ta-da, there we go. So technically what we have is a really tiny, tiny angle. Now, small angle theorem states that if you're doing things less than ½ degree, you can just axe the tangent here, and it's literally going to just be 2 over 400 is roughly what we're equal to, right? Roughly, we're equal to 2 over 400, which is 0.005 in radians. Do make sure that you're actually doing things in radians with your calculator, because we don't really like to talk about degrees very much. And beta, kind of doing the same thing over here with beta. We have a different one. We'll highlight him, I guess, in a different color. We've got this triangle here, who is a total horizontal width of 300 and a total vertical height of 4 there. So beta is going to be the same thing. He's going to be the arctangent of the opposite, 4 millimeters, over the adjacent, 300 millimeters. All right, so again, you can just drop the arctangent part, and 4 over 300 is approximately 0.0133. It repeats, so we'll just axe it to 3 decimal places there, radians. Okie dokie, so technically we probably should keep the 3. 3 sig figs, right? 3 sig figs-ish. So anyway, there we go. We got alpha and we got beta. So back to our shear strain, gamma. The original angle theta, well, the original angle theta here, he's something like this magenta color. He's 90 degrees, but I need that in radians. I need that in radians. So what, let's see, there's 180 degrees is pi radians, and 90 is half of that, so pi over 2 is 90 degrees, but in radians. Right, so pi over 2 is what we've got for A, for our original angle, and then we need to subtract off what is theta A prime. If we're looking at theta A prime here, I'm looking at this big angle. He's gonna be 90 degrees plus we have alpha, right? Plus alpha plus beta, right? That's the actual angle right here, theta A prime. He's 90 degrees plus some more alpha plus some more beta. So if you actually solve for that, we'll go through in a nice green color here and just cancel. These two cancel out, and that negative's going to distribute all the way to. So this is going to become minus alpha minus beta. You might be thinking, why minus? Why minus? Well, think back to up here for just a moment. Think back to here for just a moment. If the angle gets bigger, then our gamma, our shear strain, is going to be negative. Did that angle get bigger? Oh, yes, it did. So those values are negative. So what we're going to plug in is we have actual just numerical values for alpha, and we're going to keep our signs. So minus alpha is, perhaps should keep its color, 0.005 radians, and minus beta, beta was 0.0133 radians. So the shear strain for alpha, or for A, the shear strain for A is going to be minus 0.0183 radians. Right, they just kind of add together there. So isn't that beautiful? And again, remembering that the negative simply means that the angle got bigger. Yep, that's all it really means, is that the angle got bigger. So, okay, cool. Okay, cool. That's it. We found shear strain at A, but we're not done yet. We also wanted to find the shear strain at D. So now, kind of running out of colors here, now I want to find this angle. I want to find theta prime at D. Sorry, he's not very beautiful. Let's move him to another spot. Theta prime at D. That's what I really want to find. Okay, so he's getting smaller, so that means that gamma technically should be bigger. What amount? What amount? How are we going to do some geometry here? Well, let's just kind of see it. If I draw a horizontal line, which I would be really bad at without my ruler. If I were to draw a horizontal line here at B, notice that the angle that we have, this is just basic geometry. If the angle here is beta, then that's the same angle as here. Okay, so that's beta. So this part over here, this is also beta. And what's going on in the vertical direction? Let's turn it vertically. What's going on over here? Kind of actually already have that line, right? That's literally just D kind of going extensively out there. So let's do it in some fun color here, like puke green. Here we go. So here's that new line. What's happening there? That is literally the same thing that's going on over at A to B prime, right? So technically, this angle should also be alpha, correct? Because he's a total height of 400, and then he scooched over, how far? 2. He scooched over 2. So he's 400 up, he's 2 over, that's where he's at right there. There's 2 more millimeters with a total height of 400. So yeah, that's literally just alpha. So we still have just alpha and beta, we're just looking at a different corner. So what does D look like? What does shear strain at D look like? Again, if we're looking at it, we have theta D, who is 90 degrees, minus theta D prime. What's theta D prime? So again, we had 90 degrees. 90 degrees is pi over 2, minus, what's theta D prime? He was 90 degrees, which is pi over 2. Then we subtracted off some alpha here, and we subtracted off some beta here, and he got smaller, right? So he lost an alpha and he lost a beta. So we minus an alpha and we minus a beta, and distribute our negative all the way through. Those are going to cancel, and we're going to get alpha. Perhaps we should actually do it in our colors. Alpha plus beta. Yep, so that angle D just got smaller, right? I know you're thinking, well, alpha plus beta is a thing, but remember that positive does mean smaller, so we already kind of did the minuses, so it's literally going to be the same thing except positive this time. Positive 0.0183 radians. And again, positive means that the angle got smaller. I know, it's kind of weird to think about that it's always backwards, but seriously, that is the easiest way to just remember it. Is just shear's just always straight up backwards in every way, shape, and form. And then that's pretty much simple. So you don't have to do this part. Technically, that's what's going on. Some people might ask, hey, why did you do original minus final in that regard? Why did you do it that way, not the other way around? Again, shear's backwards. Gotta love shear being weird. But you don't really have to constantly write out that it was 90 degrees, then it 90 degrees minus the change. Literally, you're just looking at the change itself. So what change did you have? Well, you had alpha here, you had beta here. Were they both making it get smaller? Yes, they were both making it get smaller, so therefore they are both positive values. Whereas for A, we had alpha here, we had beta here. Both of them were making it bigger, therefore both of them have a negative. That's literally all you have to think about. You don't have to do all this distribute and all of this cancel and all of that other stuff. It literally just comes down to, did it get bigger or did it get smaller? And if you know that bigger means negative and smaller means positive because shear is backwards, then you've pretty much done everything you need to, and that's simple. So hopefully through all the weirdness that is shear, it's not too complex, and this makes at least some sense.